Okay, we've come to thunderstorms. We talked about mid-latitude weather. We're moving down the tropics. We do not live in the tropics. However, the tropics are where a lot of major weather develops that eventually it does impact us. You think about it, all that heat, moisture that's down there, somehow it's got to get transported north to try to smooth out the Earth's climate because the Earth doesn't like to have all the cold at the top, the poles, and all the heat at the equator. One of the mechanisms is tropical weather systems. So we're going to talk about the tropical weather systems today a little bit. First, tropics are considered anything where the sun is going to be directly overhead. So that's 23.5 degrees north and 23.5 degrees south. They just don't get frontal passages there. So all the air mass is typically uniformly warm, generally humid because there is a lot of ocean there. However, over the deserts, obviously it's very dry and hot. So typically there are thunderstorms that develop in small clusters or lines, particularly along the intertropical convergence zone. We know what the intertropical convergence zone is. That's where areas of the southern hemisphere winds converge with the northern hemisphere winds. And there's rising motion there. So with that, that's where there's thunderstorms are going to occur. One of the interesting things is we do streamline analysis many times on maps instead of just an isobaric analysis. Why do we do that? Well, there's not a lot of isobars to be had in the tropics typically. So by doing this, basically a streamline is just you following the wind. You start at one point and just try to move where the wind's going to take you, every point. And if you do that, you wind up seeing where winds are coming together and when they're diverging. So it's a great way to pick out divergence and convergence in surface weather patterns. One of the major things in the tropics are obviously hurricanes, and we're going to discuss those somewhat here. And they are significantly different than extratropical cyclones. As you have learned, extratropical cyclones have temperature contrast. Guess what? Hurricanes hate temperature contrast. Extratropical cyclones get stronger with height. Just the opposite. Hurricanes actually get anticyclones above them. So they're a warm core, typically low level circulation. Strongest part in a hurricane is the eye. Interestingly, extratropical cyclones, most intense, winds may be strongest right near the center of them. A hurricane actually is going to have an area of light winds near the center of it, called an eye. Here you can actually see a depiction of a hurricane. You see the winds coming in. Notice the bands. One band here, we'll say, another one. As the hurricane approaches, what you wind up getting is bands of showers and thunderstorms. Some of these will be thunderstorms that get progressively more intense as they come at you. So with that, let's go back here a minute. And I grabbed an image of Ian hit Fort Myers last summer extremely hard. So if you look at it, here's the eye right there offshore. The first outer eye wall is beginning to hit Fort Myers at this time. This is a Category 4 hurricane. You can see all the bubbly kind of clouds here around it. And look at the features here. If you look out, there's like another band of higher clouds out here, another one out here, and one way out here. These are all bands that are rotating into the center, just like we looked at on that image. So with that, you can actually see, they're covering all the way area, coming off of Cuba here and down, and up to the north, coming off the Atlantic and in. You can see a band right here. So Ian is a very classical hurricane with these bands rotating around it. If you were to look at radar at the same time, you can actually see one band here, another one out here, new one here, another one out here. And as this hurricane is approaching you, you're going to walk through several of these bands of showers and thunderstorms. Each one more wind, stronger rain. So that's an interesting feature. And you can see the eye wall here. Interesting, less intense rainfall at some of the points as it's getting to the land. The more intense over the water. Hurricanes love the water. So let's talk a little bit about the development, how that works. So we've just seen this depicted right on a real-time hurricane that formed. So you need some necessary things to form a hurricane. You have to have very warm sea surface temperatures. As a matter of fact, they got to be above 80 degrees through at least 150 feet. So in other words, if you could dive down in the ocean, you would be fairly warm for 150 feet. There's got to be significant Coriolis effect. Remember, the Coriolis effect goes to zero as you approach the equator. So if that's the case, hurricanes can't form at the equator. They have to be a little bit away. Believe it or not, Aruba, which is fairly close to the equator, hardly ever gets a hurricane because of this fact. There must be weak winds aloft, and the air's got to be humid all the way through, very high humidities. That means that sometimes there are factors in the tropics that where you may get some dry air involved. Or maybe the winds are a little stronger today than they were a couple days ago. All these things can impact the development of a hurricane. So where's warm water? Well, we have a lot of warm water in the Gulf of Mexico. We have what we call the loop current. Temperatures here can get ridiculously warm, up into the 90s. And they can go out as part of the Gulf Stream coming out this way. And you can see little eddies along the Gulf Stream here where warmer water is. Some of these eddies help feed and continue hurricane development as they move north. Every once in a while you'll read or listen to news reports of a hurricane moving toward the east coast of the United States. That hurricane may be said, oh, it's moving at a Category 3. However, it may develop into a Category 4 as it moves across the Gulf Stream. What they're saying is as it moves across warmer water. Coriolis, again, you don't get hurricanes within 5 degrees of the equator. The key here is you want the weak winds, very little wind shear. And that means relative to the storm motion. Say the storm is moving from east to west. Well, if the wind's aloft, we're coming from west to east, you have wind shear, it's going to wreak havoc on that storm. However, if your winds are moving with the storm, you may have a weak wind shear, and it allows these thunderstorms to develop and get stronger. And they develop into vertical. Interestingly, El Nino years usually have fairly strong easterly trade winds. When that occurs, you have less hurricanes. Here's your averages. Notice you have a Western Pacific gets quite a few storms, as does the Atlantic. And they actually increased these averages slightly over the last 30 years because of the fact that we've had more hurricanes lately. Notice where they form. You'll notice something. Hurricanes that form off of Mexico on the Pacific side hardly ever impact the U.S. They tend to stay out in the ocean and away from, you would think, oh, that close to California, they're going to come in. It's a rare moment in time when they hit California. However, some moisture from hurricanes in the Gulf of Mexico may move in. We've learned about the monsoon, North American monsoon. Some of that moisture may actually get carried into the North American monsoon to dump heavy rains on Arizona, New Mexico area. Notice all these hurricanes in the Atlantic, Gulf of Mexico, the Caribbean, all have the potential to impact the United States. Most hurricanes, our hurricane season typically runs June 1st to November 30th. What I want you to notice here is that even in May, there have been hurricanes, and in December. So that means basically January, February, March, and April are the only month that you have a really high probability, like almost 100%, of never seeing a hurricane in the tropics. You can, not saying you can't, but they're just rare. Notice the peak. Late August, early September is the peak time for hurricanes to develop. Why would that be? Well, you want the highest sea surface temperatures, remember? Remember, the specific heat of water is much better than land, much higher. So you wind up taking a while. The sun's cumulative effect won't reach its maximum until mid-August to late October. And you can see that in the way hurricanes develop. In June, they typically form in the Caribbean, warmer waters. By July, they're beginning to migrate out into the Atlantic more, coming in August as well. September, both areas very popular. By October, we're beginning to a little bit more on the Gulf Stream. So how do hurricanes form? They typically form with some kind of easterly wave, a little disturbance. Interestingly, an easterly wave that comes off of Africa has most of its precipitation. Convergence is on the east side. So in other words, as it's approaching, you have dry weather. Then it comes across and puts a band of showers. These move across the tropics all the time in the summertime. Every once in a while, there's some convective cloud clusters. One of the interesting things, the Saharan air layer, very, very dry layer. Think of it as an elevated dust storm. It develops over the Saharan desert, very dusty, very dry. What happens is also very hot. You wind up with a very hot layer of dry, dusty air moving above the moist air near the surface of the ocean as it's moving across the Atlantic. So as thunderstorms develop, these showers, really, they never become thunderstorms because they hit this dry layer. They dissipate. The dust keeps heating from occurring to heat the air below. There's a lot of wind shear there, so they're basically a hurricane or tropical cyclone killer. So, however, when a hurricane gets going, the pressure is going to begin to drop. All this water vapor condenses in the storm, releases latent heat. It needs heating. Cooling as it rises up can trigger condensation. Great convergence of air. I mean, ridiculous convergence of air. And these are the different categories. Tropical depressions are not named, but they must have winds of 23 miles per hour or higher. And they must be a circulation. In other words, you can't be just one isolated thunderstorm cell. I need to be able to see the winds going around counterclockwise. Tropical storms are 9 miles an hour, and hurricanes are 74 miles an hour. And they will go up and down in categories. Interestingly, the worst thing in a hurricane, and we saw this in Ian, is the storm surge. People don't realize how devastating these are. Rain is the next. So you're basically, isn't the wind that's killing you. It's the rain and the storm surge. You can see all the flooding here in Port Arthur, Texas from this storm, Hurricane Harvey. And remember, these storms are forming in the tropics. They're very warm. They're very, very humid. They have a tremendous amount of moisture. That's why when they come into the United States, they dump tremendous rainfalls, sometimes upwards of 50 inches, as in this case. So what are some of the hazards? We know winds can be very strong. There's a very tight pressure gradient near the center of the storm. There may be spin-up vortices in the center of the storm. We've seen these. and they diminish rapidly after landfall. What happens is the hurricane's moved away from its energy. Energy is coming from the ocean, warm ocean water. Oh, yeah, friction also plays a role. Once it hit land, friction's going to begin to slow the winds. So it loses both its energy and it gets away from friction. It hits more friction, so the winds are going to begin to drop off. However, interestingly, that's when the tornadoes might occur with these storms. Storm surge. Storm surge, if you were to live at the beach, and I happen to like living at the beach, I'm not that close, but I'm close enough. What happens is when the wind is coming towards you, towards the beach from off the ocean, and it's been doing this for a while, it's blowing the water. That water isn't stationary, it moves with the wind, as we learned with the ocean currents. So when it does, and if it continues to move towards you, it's going to be more and more water piling up by the shore. It can't come inland. It's just going to pile up, get higher and higher along the coast. So while it's doing that, it literally is raising the tides. Each tide is successively higher. We get this here in Virginia Beach from nor'easters. We get it from prolonged east winds that might happen sometimes. May only move you up a foot or two, but when a hurricane comes, all of a sudden, maybe I have 150-mile-an-hour winds over 500 miles out into the ocean. That's a lot of water that's being pushed up. So it winds up moving the water table up higher. And with that higher water, oh yeah, you're getting waves on top of it too. All of this can cause damage, obviously, be extremely dangerous to where you live. Ian was a classic example. They showed a sign in Fort Myers Beach. That sign was 8 to 10 feet up in the air, and they watched the high tide at that sign go up and over that sign, so that some of the high tide there was over 10 feet high. Well, first off, the water is moving really fast. There's going to be waves on top of that. Imagine the amount of danger that's going to cause to anybody that had been living in that area. First, their house may be getting destroyed underneath them. All of this, very dangerous. And here you can see the damage inflicted. This was Hurricane Michael on Mexico Beach, Florida. It just wipes out the first several rows and well inland. Camille had the highest storm surge, 24 feet. Katrina had a devastating storm surge. Oh yeah, Sandy, you're going to tell me about why their storm surge was so high. Look at it, 12 foot at Kings Point, which is right by New York City. Staten Island had 9 feet. The Battery had 9 feet. I want to know why. Why did that storm surge occur? There is a prediction model, SLOSH, which I worked on when I was in the Weather Service, and some other. I spent a lot of time on storm surge probability forecasts that we're now using. And these are some, obviously, interesting things with hurricanes. There's the challenge: hurricane frequency will go up and go down. For example, I went to college from 1970 to 1974. We were a bunch of idiots, maybe, but we were meteorology majors and we loved hurricanes. So we had made a rule within our group that we were going to drive to wherever hurricane came into Florida during the time we were in college. The 4 years I was at Florida State, not a single hurricane came into Florida during that 4 years while we were at college. Doesn't happen normally, but they were. What happened during is there's Atlantic Multi-Decadal Oscillation, AMO. And notice it was very cold during that time. Some of the record cold, as a matter of fact. We didn't get hurricanes. Now, we're heading we've been going the other direction for several years now, and it's multi-decadal. Really don't know how long it's going to go. It could last another 15, 20 years. We don't know that. But if it stays up in that way, we're going to have more hurricanes and a lot more problems, and so impacts it. And here are just some trends that they expect to happen if it continues global warming. Again, these are forecasts, just like any weather forecast, but they give you some ideas of what may occur. There's always a threat to the southeastern United States. People love to move to the coast. They want warm climates. They like to look at the ocean. Barrier Islands can help protect you. I was just down on the Outer Banks. The Outer Banks are a barrier island. That means that the Outer Banks, when they get hit with a hurricane, are going to take a whole lot more than if I move to the inland or the bay side. The islands may get wiped out. You'll see this cut right here, and all of a sudden the water that was in the Atlantic Ocean comes through into the bay. So barrier islands protect us. Oh yeah, people live on barrier islands. Obviously the Outer Banks are a classic example. There's an island in Virginia Beach that was developed by a hurricane that has over 1,000 homes on it now. Guess what? Probably someday a hurricane's going to take that island out. And here you can see the evacuation. It takes forever. They estimate in Hampton Roads, where I live, that if they had to do a full Category 4 hurricane, which is what we estimate maximum would be here in Hampton Roads, that it would take up to 4 days to completely safely evacuate the area. That's a long time. So that's just examples of what we're looking at in the hurricane. So I hope you got a little bit out of that, and let me know if you have any questions.